Our last topic for the organic chemistry section is to talk a little bit about what happens when we move beyond carbon, hydrogen, and halogens. Turns out there's a whole wealth of chemistry that occurs with oxygen and nitrogen primarily, and also sulfur in organic molecules. And in this class, we're not going to go over the details of each one of those. That would be like for a future class if you went on to take a second semester general organic biochemistry class. Then you'd cover the details of some of the chemistry of these things. But what we want to be able to do today is we want to be able to recognize them when we see them. And it's useful to be able to recognize these groups of common atoms. You remember those happened when we were talking about ions. We had the common ions like carbonate, sulfate. They occur so frequently that being able to recognize them and go, oh, I've seen that before, is useful in understanding molecules. And similar here, we're going to study these things called the functional groups. And they are groups of atoms that appear frequently in organic molecules. And again, we're not going to cover the chemistry. We're just going to be able to recognize them and point to them and say, oh, there we go. I've got a carboxylic acid. I know what that is. Even though I don't know the chemistry quite yet, I can recognize it and see it there. And you'll see what I mean as we go through. So what are our functional groups? The easiest way is just to dive right in and start looking at the different functional groups that we're going to talk about. The first is alkenes. And what is an alkene? An alkene is the presence of a carbon-carbon double bond in a molecule. And a molecule can certainly have more than one carbon-carbon double bond, so it can be a molecule that has more than one alkene in it. But if we were to draw, say, butane like this, and then just to stick a second line there, what does that line say? Well, I'm going to draw those carbons in there a little more now. And it says that, hey, I've got a carbon here, I've got a carbon here, and there's two bonds in between them. Doesn't change the number of carbons, changes the number of hydrogens, because now there's 3 bonds drawn from this guy, so there's only 1 hydrogen there. That's an important one. On this end, there's 2 bonds drawn from that one, so there's 2 hydrogens on the end of that guy. So it does change the hydrogens, but doesn't change too much else about the molecule, other than its chemistry, and now the fact that we've got an alkene. And so what you're going to want to do is you're going to find those on an exam, and you're going to circle those, and you're going to say, hey, I know this is an alkene. All right. It can occur at the end of the molecule or in the middle of a molecule. So I could also draw something that looked like this and put my double bond right in the middle there. Or it could occur many places in the molecule, and you can see a double bond there and a double bond there. So if an alkene is the presence of a carbon-carbon double bond, you might guess that an alkyne is the presence of a carbon-carbon triple bond. And one of the things that happens when you get a carbon-carbon triple bond is the atoms that are on the other side of it literally have to stick straight out. So it's kind of a funny thing that happens. So a simple alkene might look like this. And you'll notice I drew it a little bit funny. I left spaces here, and I didn't normally leave spaces when I drew these skeletal structures. Why did I leave a space there? Because without the space, it's a little harder to interpret what's going on. It's a little hard to know when that triple bond ends, when other things begin. So people will often write alkynes with that space in there. How many carbons are in this structure? There's 1 here, 2, 3, and 4. So this has 4 carbons in it, but it's really that presence of that triple bond here that you would circle and label, say, I happen to know this is an alkyne. The last one for this slide is what's called an aromatic. And you might think, oh, that sounds familiar. Aromatic means smelly. And it's because these molecules tend to be very smelly. Some people really like the smell of them, and some people can't stand the smell of them. If you think the smell of gasoline is not unpleasant, then you probably like the smell of aromatics. If you think gasoline is the worst smell in the world, not that you'd put cologne on or anything, but some people are just offended by the smell, and some people think, oh, it doesn't smell that bad. So an aromatic, they tend to be smelly molecules, and what they are is the presence of a ring with alternating double bonds. The most common one you're going to find is the aromatic that looks like this and has 3 double bonds in it. So the cyclohexane type ring, but now we've got these 3 double bonds in it. Double, single, double, single. People will often draw this because it occurs so frequently, just to save a little bit of time. They'll draw it like this with a ring in the middle. Those 2 structures that you see up there are 100% entirely equivalent. There's a good reason also to draw that ring. It turns out the electrons do move around quite a lot in these molecules, but either one of those is a perfectly acceptable way to draw an aromatic. You can also have aromatics in any even numbered rings. You can have an aromatic in a ring of 4, you can have an aromatic in a ring of 8, but 99% of the aromatics you're ever going to run across are related to cyclohexane taking on a few double bonds and being aromatic. Now, just to be clear, just because you have a cyclohexane with 3 double bonds doesn't mean that it's an aromatic. If those double bonds are next to each other, for 1, it's going to be very hard to do that. But for 2, it needs to be alternating single, double, single, double. And so this is not an aromatic. Our next group of functional groups that we're going to talk about are the alcohols, the thiols, and the ethers. An alcohol, very easy. It's presence of an OH group. And again, when I just put that kind of dash out there, it just means the OH is attached to something, even though we don't say here what it is because it's kind of generic. I talked briefly about isopropyl alcohol in a previous video. It looks something like that. The alcohol group right there is the OH group. But it can occur anywhere. You could have a larger molecule and the OH occurring at the end. How would we count atoms and stuff in that? Well, we count carbons the same. 1, 2, 3, 4 carbons in this molecule. So we'd have a C4. Hydrogens, 3 on this one, 2, 2, 2, and also 1 here. It turns out when you draw skeletal structures, if you have a hydrogen on a carbon, you don't need to draw it. You can, it's possible, but most people don't. If you have a hydrogen on another atom, you must draw it. So I would not be allowed to write this structure and just write O and someone assumes there's an H, because sometimes the H would be there and sometimes it wouldn't, depending on the chemistry. And so if there's a hydrogen on something other than carbon, you have to put it in. You can't leave it out. So I count 3, 4, 5, 6, 7, 8, 9, 10, H, 10, and O. When we're writing formulas like this, we generally go C, then H, then O, then N, and then other atoms after that, not as important of order. So I do C4, H10, O. The next one, a thiol. A thiol is very similar to an alcohol, but here it's the presence of an SH group. And here's a hint for this class. This is the only functional group we're going to be talking about with sulfur. So if you see a sulfur anywhere, you can circle it and say, hey, that's a thiol. So here is a very simple molecule, has a thiol at the end, and that's what you'd do, is you'd circle it and you'd label that as a thiol, or answer a multiple choice question if that's what was going on. Our last one on this page of the alcohols, thiols, was the ether. And what is an ether? It's the presence of a C bonded to an O bonded to a C. And those C's are going to have other things bonded to them, whatever. It could be more molecules, could just be hydrogens. But if you have C bonded to O bonded to C, you've got an ether. Now, what does that look like when we draw the skeletal structures? Well, it turns out when you start putting things other than carbon into a skeletal structure, you leave it some room. So you'll notice in the skeletal structure, I didn't just draw my skeletal structure and then try to stick an O on there like that, because it's unclear as to whether that O is attached to that carbon or replaces that carbon. So what we do when we're drawing our skeletal structures and we have an O in there is we actually put a little break. You'll notice I actually didn't draw the end of that triangle there, and then the O goes into that break. So we have carbon, oxygen, carbon. That is an ether group. And when you circle it, you can certainly just circle that one and call it an ether if you want to. It is technically the presence of the carbons on the other sides, but sometimes it's just easier to circle just the O part. Our next group are aldehydes and ketones. What is an aldehyde? It is the presence of a terminal C double bond OH. And again, I leave this one just sticking out all by itself because I don't really care what else is there. Some people will use a generic notation R, which stands for the rest of the molecule. And what does it mean by terminal? Terminal means it's the end of the molecule. You can't have carbons on the other side of that one. So it's carbon bonded to oxygen, hydrogen, end of the molecule right there, but you can have a huge molecule on the other side. So a simple aldehyde would look something like this. And you're like, well, Professor Clements, what about that hydrogen there? Well, I don't have to draw the hydrogen since it's on a carbon. If you look at this carbon, there's 3 bonds attached to this carbon, which means there is a hydrogen there. And in a skeletal structure, I can draw it, but I don't have to draw it. So either way, with or without the hydrogen is a perfectly acceptable way to draw this molecule. And again, you'd just be circling that end one and saying, hey, that is an aldehyde. So if an aldehyde is a terminal C double bond O, what do you think a ketone might be? That's the presence of a middle C double bond O. And then what that means is that on either side of that carbon, there's more of the molecule. There's some carbon and maybe some other things, big or small, but that double bonded oxygen is on a carbon, and there's molecule on both sides of it. How would that look? It could look something like this. That would be a ketone. See, I've got a carbon on one side of it. I've got a carbon on the other side of it. Now there's more on this side than there are on the other side, and that's just fine. And then what your job would be would just be to circle that C double bond O and say, hey, I've got myself a ketone there. So let me label that as a ketone. I don't know if you can hear the stuff going on outside my window. I apologize if it's a little loud. All right, a carboxylic acid and an ester. What is a carboxylic acid? Carbox and then ilic acid. And by the way, it's not just carboxylic. Just like hydrochloric acid and nitric acid, you have to have the word acid as part of this. You can't just say carboxylic and have people know what you mean. This is the presence of a terminal C double bonded to O. And you're like, hey, that's an aldehyde. You're about to tell me about an aldehyde, Professor Clements. And you're partially correct. But now, instead of a hydrogen on there, I've got an OH on there. You say, well, Professor Clements, isn't that just an alcohol and an aldehyde next to each other? And the answer is not really, but kinda. And the analogy I give is this. Would you ever walk into a pizza shop and say, hi, can you please give me a crust sauce cheese, please? They'd look at you funny, right? Because as soon as you put a crust, a sauce, and cheese together, you don't call it crust, sauce, cheese, you call it pizza. It's this new thing because it's together, and you don't call it those old things anymore. You might say, oh, my pizza has some cheese in it, just like you say my carboxylic acid has an alcohol in it. But you call it a pizza, just like when these two things are together, we call them a carboxylic acid. So what that looks like, if you're drawing it, is something like this. And when you were circling it and labeling it, you circle that entire thing, the double bonded O and the OH together, not two separate circles. If you label that as an aldehyde and an alcohol, I will mark it as wrong because it is incorrect to call it that. It's a pizza. It's a carboxylic acid altogether. So that is terminal C double bond O with OH. And then what do you think an ester might be? And by the way, ester does sound awfully close to ether. I wouldn't have named those two so similarly, but somebody did, and I wasn't in charge. Here we've got the presence of a middle C double bonded to O with an O, right? So it looks very similar to a carboxylic acid, except we're missing the hydrogen. That's because we're in the middle now, and so we've got to have molecule parts on both sides of the molecule. It's just got to be at least one carbon on either side and maybe some more, and that is an ester. So I could draw an example of an ester, which would look like this. There's a double bonded O next to an O, and there's some more molecule beyond the end of that. What you'd do is you'd circle this one, and you'd call that whole thing an ester. Now, an ester does look an awful lot like a ketone plus an ether, and it kind of is, but at the same time it isn't, because it's a pizza. It's all together. When you put those two things next to each other, they become an ester. They are no longer their individual parts of a ketone and an ether. We're almost done. These are our last two, an amine and amide, the amines. It's pretty easy. Presence of nitrogen. When you have presence of nitrogen, you have an amine, unless you have an amide, which we'll get to next. So if I had a molecule and it looks something like that, that would be an amine. Now here's a problem. We know nitrogen always makes 3 bonds, and so we have to specify that there's a hydrogen on there. You're not going to need to do that. You're not going to need to draw any of these and know that that hydrogen's there, but I'm telling you, you got to put that there. So that nitrogen's there. We've got an amine because we've got nitrogen present in our molecule. And we can have more than one nitrogen present, and then we'd have more than one amine. So what's the difference between an amine and an amide, an amide? This is the presence of a C double bonded to O bonded to nitrogen and things on the other side. Doesn't have to be carbon. It could be hydrogens on that nitrogen. So if we drew something that looked like this, that would be an amide. We've got that C double bond O next to an NH2. So it turns out our C double bond O is a pretty important molecule. It's one or component. We need to look for it. And then if you have a C double bond O, what you need to do is look on either side of it. What's the next atom over from that C double bond O? If it's an oxygen or a nitrogen, then it's one of these special groups, which is an amide, a carboxylic acid, or an ester. If it doesn't, if it's just carbon on both sides, then you probably have just a ketone or maybe an aldehyde if it's terminal. So be aware of that. Anytime you see a C double bond O, you need to look on either side of it to see if you have one of these special pizza type molecules. Because an amide is just the presence of an aldehyde with, a ketone with a amine. But when you put it together, it's this new thing called an amide. What we're going to do in the next several slides is I'm going to show you examples of this. Then I tried to pick molecules that were actually relevant, that are actually real molecules you see in the world. The molecules we're going to see here are a bit more complex than ones I'd give you on an exam, and sometimes they're very large molecules, and I wouldn't make you do large ones, but we're going to talk about them as we go. So the first one we're going to look at, and if you can kind of see it on the screen there, is lycopene. This is this big, long molecule with lots of double bonds. Now again, I wouldn't give you a molecule this big, so we're just going to circle a couple of them. But if I give you a molecule with 2 or 3, you would label each of them. And when you have double bonds, what are they? They are called alkenes. Now some people look down here and they say, Professor, is that an aromatic? And the answer is no, for 2 reasons. 1, it's not actually connected. It looks almost connected. And 2, there's not alternating double bonds. There's 2 double bonds, but there'd have to be a double bond here and it be connected for it to be an aromatic. So in this one, we just have a bunch of alkenes. It's an antioxidant that's present in tomatoes. When you eat a tomato, there's plenty of antioxidants in it, and one of them is lycopene. What's funny is you read a ketchup bottle nowadays, and they advertise it as this amazing antioxidant stuff, but you know, it's just ketchup, folks. It's not amazing. It's not wonderful. It's ketchup. Yep. The next one is one of my favorite molecules. I mentioned this, I think, in one of my previous videos, that everything you see comes down to one molecule. And that one molecule is cis-retinal. Cis-retinal looks like this top molecule here. The little bold that you see is not important. It's just showing you which atom or which bond is breaking. So what we're going to look for is the presence of functional groups. Certainly, we see some alkenes in here. And again, you'd circle all of them on a test or things like that. I'm just going to circle a couple and label them. I wouldn't give you this many. But what else? Well, one thing to look for is anytime there's oxygen, sulfur, or nitrogen, you better be circling that and labeling that. So I see an oxygen over here, and I got to figure out what I'm going to label that as. And when I look and say, okay, it's an oxygen at the end of a molecule, there's just a hydrogen there, this is an aldehyde. So what happens in the back of your eye is cis-retinal is on the top of all those different parts of your eyes, all the different colors. People have probably told you that there's different parts of the eye that see different colors, and that's entirely true. But on the top of each one of those is cis-retinal. And cis-retinal receives light, and it changes into trans-retinal, which causes other changes that your brain then interprets as seeing something. So literally everything you've ever seen in your life comes back to a molecule changing from something that looks like this and rotating to something that looks like that. That's everything you've ever seen. You don't actually see anything. You see the effect of a molecule rotating, and your brain interprets that as you seeing something. Crazy! I love it. Okay, we got everything in there. A few more alkenes, but we're not going to label every one. Our next molecule, definitely a little simpler looking. And this molecule, if you like the smell of raspberries, this is the smell of a raspberry. Oh, I love the smell of raspberry. It's very subtle, but it's a very good smell. And this molecule is fairly uncommon, not uncommon. It's fairly dilute inside a raspberry. There's not a lot of it. And so if you actually get this one naturally derived and extracted from raspberries, it's one of the most expensive odorants in the odor industry. And this stuff can cost about $25,000 for a kilogram. $25,000 for a kilogram of this stuff if it's naturally derived. Amazing. So what do we see in there? Well, remember, anytime we see an oxygen or hydrogen, we better be circling it. So we see an O there. We see an O there. What's this one on the left? An OH is an alcohol. And the one on the right, is it terminal C double bond O? Or is it a middle C double bond O? We look on either side of it, and there's just carbons there. There's no special oxygens or nitrogens. So that must mean it's in the middle. And if it's in the middle, it's a ketone. Okay, we circle all the oxygens. Are we done? No, there's some double bonds there. Now, what we don't want to do is circle each double bond and say I've got 3 alkenes, because when you put them together in this one big thing, it's a pizza, and that pizza is called an aromatic. So this molecule, the raspberry smell, has an alcohol, an aromatic, and a ketone. Our next one, this is the smell of Starbucks. When you walk into a coffee shop, you smell the smell of roasted coffee, and this is one of the primary smells that you smell. What do we see in it? Boy, sulfur really stands out there, doesn't it? And the only thing we have with sulfur is a thiol. This oxygen stands out too. We should always circle oxygen. What's on either side of it? Carbon here, so it's an oxygen in between 2 carbons, and that is an ether. What do we have down here? We've got 2 alkenes. Is this an aromatic? The answer is no, because it's only got 5 atoms. You have to have an even number of atoms to have an aromatic, because we've got 2 single bonds in a row, and so that's not alternating double bonds. This next molecule, I would never ever give you this molecule on a test. There are 2 overlapping groups, but again, I wanted to give you actual real ones. This is one of the primary flavors of yeasty foods. So if you like a yeasty bread and you like that flavor, this is one of those flavor molecules inside the yeasty product. Now, we're going to pretend these two are not overlapping, that these are separate groups. What do we see? We see a double bonded oxygen next to an oxygen. That has a special name called an ester. And again, I'd never do this to you on a test, but also on this one is a double bonded oxygen next to a nitrogen. And if that were all by itself, you'd call it an amide. And so we've got an amide and an ester kind of in this one. Little overlap. I would never overlap things on a test for you. If you ever see something on a test that looks like it's overlapping, see if you can reinterpret it, and maybe it's one thing that's a pizza instead of these two overlapping things that you might be thinking about. All right, our last molecule that we're going to practice on is this one right here. And this is one of the primary molecules responsible for the taste of a Cabernet Sauvignon. So if you like that kind of wine, that's what it is. I don't particularly like wine, so I don't particularly like this molecule, but that's one of the flavors that you're getting. We see some things really quick. We see nitrogen in there. And again, I wouldn't give you this one on a test because there's some overlapping things. But when we see nitrogen, we look on either side. There's no C double bond O's. These are just amines. We see an oxygen here. Now, what kind of oxygen is that? Well, let's look on either side of it. Remember, in this condensed notation, the OCH3 means the O is bonded to the C. On the other side, the O is also bonded to a C. So we've got an oxygen in the middle of two carbons. That is an ether. And then lastly, we've got these double bonds here. Do we have three alkenes? Nope. If they're part of a ring with alternating double bonds, this whole thing is called an aromatic. So we've got an aromatic, a couple of amines, and an ether. And again, I wouldn't give you this one on a test because it's got overlapping parts, but it's an interesting actual real-world molecule using these functional groups. So that's what I would expect you to be able to do, is identify circle functional groups, or obviously just find them if there's a multiple choice question or something like that. Thank you. Have a great day.